Sorry for the delay. I first want to just thank Sembra and their partners for inviting me here. This is a real privilege for me to be here today. And I also have to thank the people taking care of us this week, especially Lieutenant Commander Diogo, Private Bruna, and of course Captain Federico, who helped me with some visa issues I had last week. So I'm very lucky to be here in many ways. So today I want to talk to you a little bit about a lot of the talks today, the last couple days have been about large-scale commercial operations, very large ROVs, large AUVs. Well, size doesn't always matter. So in our field, we use a very small AUV, the Remus 100, and it's just as important in our operations as it is in the larger operations. And specifically, I want to talk about using these AUVs in dynamic environments in the US. So first, what is on our vehicle? Well, we have the usual sensors, conductivity, temperature, and depth. We have an ADCP to measure currents. And then we have a whole suite of optical sensors. So we have backscatter, rhodamine, chlorophyll, turbidity. But what we end up using most for our work is CDOM. And if you're not familiar with CDOM, CDOM is color dissolved organic matter. And it's the optically measurable component of dissolved organic matter in water. So we use this as a natural tracer. So I only have time today to talk about a couple projects that we've done. And they're about using CDOM as a natural river tracer to track estuarine discharge, and then also using CDOM to track discharge from ocean outfalls. So this is some work we did a couple years ago in North Carolina. And it shows the bathymetry map here. You have the new channel, which is the dredge channel they use for navigation, and then there was an older dredge channel. And this is adjacent to Camp Lejeune, one of our military installations. And the purpose of this work was to try to understand this very dynamic inlet. So sand is moving here constantly on a daily rate, and these channels become dangerous. So part of our work was to understand this so we can better model it, better predict where the sand was going to move. And so our job was to use the AUV to better understand this so we could have better boundary conditions for models. So what you see here are the AUV tracks that we chose to study this inlet. So what I was interested in, I wanted to know how this discharge out of this inlet interacted with the ambient ocean. What kind of turbulence did you get? What kind of mixing did you get? And just kind of understanding the physics that was happening in that environment. So this is just a study map showing the area. You can see our transects here from the Remus, and here's your inlet. Now, we used two separate paths when I designed this mission. Now, I told you the Remus has a ADCP on it to measure currents. So we know we can get really good current data by flying in a constant depth. But what happens when the vehicle starts undulating, moving up and down, that velocity data has a lot more errors that you have to account for. You have to account for the vehicle movement, and you have to correct the data. So the initial goal of this work was to see how well we could get velocity data when the vehicle is doing this kind of movement, because these are the type of missions that we need, because it profiles the entire water column. So you get all your scalars, you get CDOM, you get temperature, you get salinity in the entire water column. So again, this is only about 8 meters of depth. So we're not talking about very deep here. So it's a very shallow environment. So with that said, this is the only math I'm going to show you. Essentially, you just got to imagine when this vehicle is moving up and down, your ADCP measurements aren't vertical. They are over here, or they're over here. So you got to correct for that. So this is ideal when the vehicle is moving in a constant depth, so you can easily calculate velocity. But when you get this kind of movement, you got to account for it. And so that's all this is doing. It's a rotational matrix. Long story short, we were able to get good velocity data in both cases. So why is this important? Well, now we can come up and really start understanding some of the data. So what you're looking at here, this is surface current depth averaged surface currents, the top 3 meters of the water column. So the red is the actual real data from the Remus vehicle. And then we can use an interpolation scheme, and a very common one in meteorology and oceanography is objective analysis. And essentially, you're just taking all the data, the real data, and using that to come up with a best estimate of what the velocity is where you don't know it. So essentially, we can come up with this entire velocity field just from our transects that we did here. And what you're seeing is, remember the inlets up here, this is at a maximum ebb tide, so you're seeing high flow coming out of the river as well here. This was a mission we did flying perpendicular to the shoreline. So this is an idealized case from McDonald and Geyer from a paper published by them. And what you're seeing is you're seeing the fresh river water coming out here. And the way they define these zones, they define this zone here as the near field. And the near field is, by their definition, where the composite Froude number is greater than 1, which is simply just the ratio of the velocity of the current, and then the depth, and then a reduced gravity term. So essentially, all it's saying is if my momentum is stronger than the buoyancy force is, then you get a Froude number greater than 1. So this is where you get all the turbulent mixing. That's where everything happens. So this is the area we're really interested in. So you get your freshwater comes above your saltier salinity, or the saltier ocean water, and you have your idealized case up here. Now what I'm showing down here is we're seeing the exact same thing using CDOM as a natural tracer. So again, we're seeing this liftoff from the estuarine discharge. We see the transition from the near field to the far field. Now, if you weren't using an AUV, this would be almost impossible to get. So the mobility in AUV and the resolution of the data you're getting allows you to see things that you can't get from point measurements or casting. So what we can do now is I have a whole velocity field I calculated. I have the Froude number that I can calculate for the entire field. So we can get a sense of how this estuary reacts once it hits the open ocean. So I picked 2 missions we performed in May of 17th and May 19th. And they're polar opposites. On the 17th, there was no wind, no waves, nothing going on. And so you can see this is our definition of the near field where the Froude number is greater than 1. It comes out to about this transect 3, which is around 1,000 meters from the inlet opening. Now, on the 19th, it was the opposite. We had a very strong northeast wind, 2-meter waves. We were the only boat that made it outside of the inlet that day, and it was a small boat, so I remember it very fondly. So we had this strong northeast wind coming in this direction, and that northeast wind actually extends that near field by about 200 to 250 meters. So this is just giving you an example of how your ambient ocean conditions can actually affect the discharge and this definition of near field to far field. And again, we wouldn't be able to get this type of data very easily without the mobility and the resolution of an AUV. So another way to look at that, notice here I have 1, 2, 3, 4, 5. I have each transect labeled by a number. Well, we can correlate that spatially by looking at profiles of each transect. So this would be the transect 1, closest to the shoal, and then you can see the evolution of the plume as it moves offshore. So what you're seeing is you're seeing the discharge here, lower salinity value, and then you see how it moves offshore. So what I want to show you here with each case, which is interesting, you can first see how stratification plays a role in what happens to the plume. So on the 17th here, you have this curve. So you have a stratified water column. So what that's doing is that heavier water is capping the plume depth. It's pushing it up. It's not letting the plume go beyond 2 meters. And so as you see this evolve offshore, your max depth is around 2 meters, maybe 3 meters. But what happens on the 19th here, when you have a very turbulent environment, very high winds, big waves, you get a well-mixed water column. So what happens there? Well, now your plume can stay at depth. So you'll notice this plume depth is almost twice this depth. And you'll also notice the mixing that's going on. So as this plume moves offshore, the concentration stays relatively the same. In this case, you can see the concentration gets significantly lower. So that's telling us we have a very turbulent environment. And the ambient conditions from the wind and the waves play a very important part of what's happening to this discharge as it moves offshore. Now you may also notice, if this is the ambient conditions over here, we have another salinity signature over here. So what is that? Where is that coming from? And I kind of broke this apart by numbering it again, 1, 2, 3, 4. So you can see almost what looks like pillars. So there's some interesting structure going on here. And again, when you just look at this map by itself, or these graphs by itself, it's hard to determine exactly what's causing that. But with the luxury of an AUV and having all these synoptic measurements, we can kind of put the puzzle together. So what's happening is you have your ebb flood coming out here. This is during the very strong wind coming out of the northeast like this. So you have old channel flow coming out of here, and it's actually turning and getting pushed in, advected in to the new plume. So what you're seeing is this signature, salinity signature, is coming from this old channel. And now that we have the velocity measurements, we can confirm that. So what you're seeing is, here's your wind direction. These points, 1, 2, 3, 4, correlate with the structure here, 1, 2, 3, 4. So you have a strong northeast wind pushing down coast like this. It advects that salinity back towards shore, and it actually creates an eddy between the old plume, which is here, the old channel, and the new channel. And essentially that water is just being rotated around that eddy, and it eventually mixes at about transect 3. So the important part about this is, again, you take one of these maps by itself, you're not going to know what's going on. You can guess, you can try to figure out what's going on, but because we have all these different data sets taken at the same time synoptically together, we can put the puzzle together and we can really understand the dynamics of what's going on. So another way we use our AUV is mapping ocean outfalls. So what you're seeing here is just a little illustration, a cartoon of, okay, you have this wastewater discharge out into the ocean, you have some ambient current affecting it, and basically, how are we going to measure that? So it's similar to the estuarine discharge. You have the near field, which is rising here. It hits its equilibrium depth, and then this would be defined as the far field. And the only thing that's going to affect that plume in the far field would be some external mechanism. So essentially, when you hit this equilibrium depth, it's a very stable environment, and you're not expecting much to happen. So what we've been able to do is use the AUV to target these plumes and try to understand the fate and transport of it. So the biggest challenge when you're trying to find wastewater from any discharge pipe is, where is it going to go? So we've developed this method using a buoy with an ADCP looking down, and it's connected to our lab through an Iridium satellite link. So essentially, before we plan any mission, we look at the currents the day before, the day of, the hour of, to determine where the plume should go. And we actually develop these real-time products called, well, this is just a profile here. So you have 0 to 100 meters, and then you have your east and west component of the velocity here, and your north-south component of the velocity. So you can see the whole velocity profile in a near real-time manner. And then we actually can come up with a particle trajectory map. And what that is essentially you're just taking your ADCP data, your current data, and projecting it in time. So the color code here, this is 48 hours, and this would be 1 hour. So essentially, we're using that velocity data to tell us where the particles are going to go. And so now, based on this map, I can make a path for my AUV that optimizes my sampling inside the plume. So we don't want to waste time sampling up here because we know the plume's not there. So this methodology is becoming very common in California. We've been directly responsible for getting wastewater treatment plants to implement this type of methodology so they don't waste time. They spend countless hours on boats doing casts and measurements they don't need to do. But with this type of methodology, you save time and money. So this is just some of the results. Again, CDOM was used as our primary tracer. So this is actually wastewater coming out of a outfall 90 meters at depth. And we're seeing it. So we did bi-monthly surveys, so 2 surveys a month for a year. So over 24 surveys to determine where this outfall sends its plume. And for over 24 missions, we saw the plume every time. So we had a 100% success rate of tracking the plume and determining it. And you can actually see this example was over 6 kilometers, and we had some mapping over 10 kilometers. So we weren't held back by the life or by how far we could see the CDOM signature. We were limited by the 8-hour battery life of the REMIS. So this type of methodology to track your ocean outfalls proved very feasible. This is just a dilution. We also did dilution where we measured CDOM on the land side at the plant, and then we could calculate a dilution based on the concentrations we saw in the water. And this is just dilution based as a function of time. So as we expect in a near field, you get very quick mixing, turbulent activity, and then in a far field, very slow mixing. And this is exactly what we expect. So what we didn't expect, well, in this case, this is each transect. So this will be closest to the outfall plume at 2 kilometers, then 3 kilometers, 4, and 5 kilometers, so getting further away from the plume. And what you're seeing is your rise height, your equilibrium depth, stays about the same as you move further away from the outfall. Now, in this example, this was just a near field. Well, it was beyond the near field, but you can see there was a lot of mixing going on, and there's this 10-meter rise in the plume. So this is unexpected. So you don't expect, when the plume hits its equilibrium depth, you don't expect it to move that much, and you don't expect it to mix that much. It's a very slow process. But in this case, it was mixing a lot, and you saw a significant rise in the plume height. And after we did a little more digging, there were internal waves coming through this study area. And the internal waves were actually mixing the plume and pushing it up in the water column. And again, we would not have been able to figure this out without all the measurements of an AUV. This is just a vertical distribution. So this, essentially, the government or the state organization we were working for wanted to know how high this plume was going to rise. Was it ever going to surface? If it surfaces, is it going to go to a beach? Do we have to close the beach? These type of public health concerns. And what we were able to tell them was, due to the extreme depth of this outfall plume, you didn't have to worry about it surfacing. It very rarely reached 30 meters, let alone 50 meters. So that comes into play with getting regulations and permits and that kind of paperwork and being regulated by different organizations. So I'm not going to read all this. The main conclusion of what I just showed you today was basically the AUV really is the only tool to kind of put the puzzle together and the work that we've done. We would not be able to figure a lot of these projects out without it, because you need those synoptic data sets. You need to know the velocity at the same time as you need to know CDOM measurements, temperature, and you can put a whole suite of instruments on these mobile vehicles, and they're essential in understanding the environment. So just a little plug here. These are some publications that we had from the work. If anybody's interested, I'll be happy to send you. I did want to end with a quick movie. I'm not sure how much time we have, so we probably won't be able to watch all of this, but we do have other applications that we use for historical mapping and some coral reef mapping. And this is work that's going on off the coast of Philippines in Palau, and there actually is a group there right now. And we actually use GoPro cameras. We have a relationship with GoPro. So we have a whole suite of GoPro cameras on the vehicle, and they give you images like this, high definition images of coral reefs. And we use this to kind of map the health of the coral reefs in the area. And we also use it for historical surveying. So I'm going to kind of forward through it here so we can give my colleagues some time. But this is the deployment of the vehicle. What's great about this for us is that you can deploy the vehicle with 2 people. So we don't need any complicated instruments, complicated huge shifts. We can use a small dinghy, and we can release the vehicle with 2 people. This is very important for us because we're going all over the world, all over the country. We need that kind of mobility and that kind of ease of deployment. So what else we got here? So this is an example of some historical mapping. We actually, the project they're doing in the Philippines right now is with a group that is looking for old World War II aircraft wrecks or shipwrecks. And essentially they're trying to give closure to families that have no idea what happened to their loved ones. And they've been very successful using not only side-scan sonar to kind of find targets of interest, but then to use the high-definition cameras to confirm what they're seeing. So this is just a couple images of some of those, some of the planes that they're finding out there. And then I want to end with, if I can find it here. Things don't always go as planned. You know, we like to say everything goes perfectly. Well, sometimes it doesn't. Sometimes your very expensive vehicle goes missing. So what do you do when your vehicle goes missing? Well, fortunately, they have a lot of recovery mechanisms to find these vehicles. And this is just a couple of examples of when our hearts stopped for about an hour or two before we found our vehicle. So the Remus is very good navigating undulating terrain, but sometimes you can't plan for some of the obstacles it'll find. And there's nothing more scary as a deployer than to see your Remus show that error message and to see that it's at depth and not at the surface, because then you know you may have some trouble. Now this one took us over a day to find, so we were convinced we lost it. Somehow it found its way into this very, very narrow crack. But it actually has like an acoustic pinger. So that's what helps you locate it. So once you're within 1 or 2 kilometers, you can typically narrow in on the vehicle itself. All right. That is the extent of my talk. I'm going to hand it over to a colleague now who's going to talk to you a little bit more about how we use ROVs as scripts. So thank you for your time.
Organized it. You've been very hospitable, and I think everything's gone very well, and you're off to a good tradition. If we can find the next presentation, we'll try and go quickly and get back up on schedule. I'm seeing it here. Okay. My name is Woody Sutherland. My colleague James Turnbull. We're from the Department of Shipboard Technical Support at Scripps Institution of Oceanography. As you heard earlier, Scripps is comparable to GEMS Tech. We have about 1,800 people, 1,800 people working there, working on lots of different projects. So it was hard to figure out what we would present today on this first annual symposium on underwater vehicles. We decided to talk about a new ROV that we're operating in our department. My department provides instrumentation and technical personnel on the 4 ships operated by Scripps, but we also contract out on ships all over the world. So we're working on other U.S. ships as well as foreign ships. Over the years, we've had lots of experience with ROVs, AUVs, and now even more so unmanned aerial vehicles that are being used. And a lot of that work was with the larger ROVs, the Jason coming from Woods Hole, the Remus from Canada. We've had ROVs from other European countries. And we kept being asked by scientists using our ships why we didn't have an ROV to offer to them. And so after many, many scientists asked, I decided to go ahead and try and get funding for an ROV, and this is just a little story about what we've done to get the funding and then get the ROV going. So some of the considerations, you heard that the Jason can operate down to beyond 6,000 meters. We didn't want to get in competition with them. When Jason mobilizes on a ship, they have two 20-foot containers they use as a control van. They have a number of other containers they have to put on the ship for supplies and workshops. We wanted to keep it very small. We found out that a lot of the scientists wanted to work in water depths around 1,500 feet, 1,500. So we decided to go with a light work class ROV. We could operate with 2 to 4 people, keep everything nice and flexible and transportable so that we could use it on our ships, take it off when it's not needed, and then move it to another ship. So the size, again, we wanted to keep it small. Operating depth, somewhere less than 2,000 meters. I knew that I had to create a budget and present that to the funding agencies and get it approved, so that had to be reasonable. We wanted to find a manufacturer that had good support, that was reliable, that was flexible, so we could change the tooling on the ROV from one cruise to another, put on geological instruments, then put on biological instruments. And we wanted to be expandable so that we could start with just a base system and then add as we got more experience and were able to get more funding. So that's what we came up with. Okay, one of the things that we first considered was how we were going to make the ROV move through the water. Doing a little research, we found that most of the ROVs in that size range were using electric motors, but we did find a couple of manufacturers that are using hydraulic motors. And by talking to engineers in the department, we were convinced that the hydraulics gave us a lot more thrust for the effort. And so we did go with the manufacturer with the hydraulic thruster. We selected deep ocean exploration and research. At the time that I got funding, we were in a period where the US dollar wasn't doing so well with other currencies around the world, so that eliminated most of the foreign manufacturers. We would have gone with a foreign manufacturer if we could afford it, but because of the exchange rate, it just wasn't likely. So we found a manufacturer in the United States up in the San Francisco area. The company was founded in 1992 by Dr. Sylvia Earle, a very famous U.S. Underwater scientist. She's done a lot of diving, scuba diving, a lot of human-occupied vessels. In 1995, they expanded to manufacture ROV and customize ROV, and in 2003, they moved into their present facility, which is quite large. So talking to them, we designed our own ROV. So this was the first production model in this class. 2,000 meter operating depth, the in-air weight's less than 500 kilograms. We needed a moderate payload so that we could go down and collect samples and bring them to the surface. With the power and the hydraulics that we had on board, we decided to go with 7.5 horsepower thrusters, the 5-function manipulator arm, and then data and video channels. Started off with just using a few of them, and now we have that to expand so that we can add additional sensors. So this is what we got. You can get a better idea of the size a little bit later, but it's easily deployed, easily recovered. The 6 thrusters, the manipulator arm, and a few cameras. And so now that I got the system, I turned it over to the engineers to operate. So I'll let James tell you about that.
Thank you, Woody. Good morning. My name is James Turnbull. I work for Scripps Institution of Oceanography, and I'm honored to be here. I want to thank SEMBRA and the organizing committee for inviting me to speak. So as Woody detailed, and to pick up where he left off, this is the nursery of the ROV. It was made in a shop in Alameda, California, which is just south of San Francisco on the central coast of the United States. We have a 5-axis manipulator that was machined or designed and machined in the manufacturing facility for which you see a picture. The unit that was shipped to us is complete on a pallet, along with a winch that was designed by another third-party company, Renmark Pacific, whom handle mainly air cargo support equipment. And the cable that we purchased was another third-party vendor, about 1,000 meters of combined fiber optic and copper conductor for power and communication. So Woody had mentioned that we are somewhat modular. We don't have a large footprint on a vessel. We require one 20-foot or roughly 6-meter cargo container, standard size, for which we have outfitted with a control room inside. And we can ship the ROV and the winch, which you saw on the previous slide, in another container. So we have outfitted that to completely be customized with what we wanted it to be: a panel of control screens, a manipulator, operator's chair, a pilot's chair, and in the center we have a rotating chair for the navigator. And training has been brought up previously yesterday about how a program can start and have training. We give opportunities to graduate students, principal investigators, research scientists to participate in the planning of their operations on a daily basis, sometimes a minute-by-minute basis, to have them in the control van with us and incorporate them into the full operations, which requires a bit of finesse or nuance. We get many personality types, and in order to interface with anyone from graduate students to principal investigators, it takes quite a bit of diplomacy and prior planning to get those things to enmesh. We have electrical and communications in the van. It's designed essentially to be plugged into the ship's power, and that's it. That's all we need to use to operate. But we can certainly interface with the ship's communication systems, internet, GPS, as well as any other communication systems for video distribution around different parts of the vessel. And we've essentially assembled it in-house. This is a nice clean picture of it. And the power distribution for the ROV is actually power transformers from ship's power come in, and we ship about 15 kilowatts down to the ROV at peak power. And that includes all the thrusters, video cameras, sensors, and auxiliary systems. We have a forward-looking sonar, which is a product developed by yet a third-party company. And we get some very high-resolution sonar images, which we offer as a product to the science party, and the data that we turn over and fully incorporate to them. It's a 900 kilohertz system with a 100-meter range, effectively good range, 60 meters, and very high resolution. And here's an image from the manufacturer showing a sunken vessel. We have a CTD that we can install on board. It's a modular system. The entire ROV is somewhat modular. We have capacity expansion for auxiliary equipment that's both hydraulic, electrical, or any other instrumentation that the science party talks with us about fitting to the instrument or fitting to the ROV. We can really accommodate many different types of custom PhD or graduate student projects. But the CTD is a very common, so conductivity, temperature, and depth measurement. It's a very common instrument in oceanographic research, manufactured by another third-party company, and plugs into our ROV system to communicate via serial feed back to the main control van. And so there are options for expansion on the auxiliary channels to continually plug in more instrumentation. We are only limited by power consumption, plug-in ports, and weight. So we can go to about 1,000 meters with the ROV currently, but our sensors are rated for greater depth. So I have a brief video to show, actually 2 brief videos. This is about our first dive in seriousness in October 2012. off the coast of Baja, California, 100 nautical miles south of San Diego. Here you see the deployment of the ROV. We really need only 4 people, 3 at the very bare minimum to deploy. It weighs 900 pounds, or about 400 kilograms in air, and we can handle a payload capacity of about 50 to 75 kilograms, depending on the weight distribution around the vehicle. So this is a manipulator camera for which we have an operator in the chair, a principal investigator on the right side of the screen, and my ROV pilot. This is obviously a standard definition video, and we have since upgraded to a high definition video, for which I'll show. This particular investigation was a geological and geophysical survey, so we ended up with about 1,000 kilograms of rocks dredged up, and the ROV recovered 1/10 of that, but we could pick which rocks the scientists wanted. So we've upgraded now to a 2,000 meter capacity, so we can go for 2 kilometers. We are limited in dive time only by the endurance of the pilots, so we get 8 to 10 hours, and then we have to recover and go to sleep for the next day. We are getting a new cable for electro and fiber optic communications. We've had a new sample box installed, and we have an HD camera. So I'll give you a brief overview. This is the sample box deployed. On a cruise, it has a hydraulic actuation for extending and retracting, and all of the instrumentation and manipulator arms are not obstructed by it. The ROV is approximately 1 meter long by maybe just slightly less than 1 meter tall. And so this is the final video for which I will conclude. This is a cruise off of Alaska in North America. It's western Canada by 200 to 500 meters depth. A number of stakeholders, principal investigators participated. You can see in the very exciting high definition video, we were doing surveys for coral reef, cold water, deep water coral. You'll notice that there are lasers that we have attached to the main camera, 15 centimeter distance apart, to allow for size surveys in the planar field of view. And the chief scientists were sampling, doing genetic testing on this species of coral, is Primnoa pacifica, a very slow-growing cold water coral. And we would take pieces of this and insert them into the sample cores and retrieve them. And the largest sample that we did retrieve was 2 meters by 1 meter. And we picked it as a bouquet of flowers as a last sample. You'll see market fish, very important economic fisheries in Alaska is quite big, and part of this was a biological survey to do video surveys as well as sample collection to determine the ecodiversity of these systems. So in conclusion, I work with a team of 4. There's 1 computer specialist, 1 deck specialist, and 2 general technicians essentially, but we all wear different hats, from computer programmers to plumbers fixing hydraulics. It's a bit like working on a car, only it's a very expensive car, as well as interfacing with scientists and having some diplomatic relations with them. It's just been an honor and a pleasure to be a part of this program for the last 2 years. So I'll be happy to take your questions, and I appreciate your time, and thank you again to Sembra.